Okay, let's start. So, good afternoon. I sent an email around about kind of the schedules for rest of the quarter. So, just to reiterate that, I'll be making use of the Friday slot, partly because I'm going to be missing one lecture. Well, I'm technically missing two lectures, but one of them would be a guest lecture. But the other one, which is Tuesday, March 5th, is no lecture. So we are kind of compensating for that. Topic-wise, so today I hope to wrap up the time and start on wireless, in particular to talk about Bluetooth LE. But before that, I'll give a sort of a broader view of IoT-related wireless technologies. So that's the agenda looking forward.
Like this week,
Every Friday, yeah. So
this week's Friday
also. Yeah, okay. The other thing is I had your stuff and a robot. That's you, okay? So that's with Leon. It's a tiny robot, okay, but I think for your purposes might work. But if not, we have to look for something else. I have a bigger robot also, but we'll need to buy a lead acid battery for that. So yeah, so try it out. Again, so this when you have checked it out, just again drop me an email that you're the list of items that you're checking out. Okay, great. So last time at the end I had started talking about 1588, which is the precision timing protocol. This is kind of the current standard for precise timing. So NTP, which we kind of sort of looked at under the hood, NTP is very complicated, obviously, is one which is used to maintain time for kind of over the internet. PTP started out for more specialized applications, like factory automation, stuff like that, where you need microsecond level, and I guess people have pushed it into sub-nanosecond, like I was describing with entities like CERN and all. And one of the things that PTP did was they really emphasized time stamping. So the challenge with NTP was it was kind of designed to run from your NTP client and servers, they all kind of run the user space on top of Unix, Windows, these kind of operating systems. So the time stamping is done at that level because these operating systems do not provide any mechanism to say, hey, I'm sending this packet, and by the way, it would timestamp it on the way out because the hardware support wasn't there. But then as part of 1588, they kind of emphasized that, network controllers, network interface cards should have that timestamping ability, and that led to emergence of 1588 compliant Ethernet chips, which basically, as the packet is going, they can timestamp it. They have a precise clock on the network interface card, and then they expose that clock to the host computer by some mechanism, as well as a timestamp. So the timestamp just gets appended to a packet, or maybe sits in a register, and you kind of talk to it. So somehow that timestamp information. So receiving CPU can learn the timestamp at which the packet was received, not at the software layer, but right at the network interface card. And likewise, when you are sending a packet out, you can acquire the timestamp for it. Now, in very slow systems, you can imagine timestamp being done as part of an outgoing packet. That is, you're sending the packet out, you timestamp, you put the timestamp at the back of the packet, compute the error code, CRC code which is attached, and send it all out. But with high-speed links, that's pretty hard to pull off. So PTP kind of catered to that as well, and which is why it has a more expensive message exchange. Even though we are still acquiring 4 timestamps, but you need 4 messages for doing it, because you send out a message and the sender gets the timestamp from the hardware, and then it sends another message carrying the timestamp. Whereas in NTP, since you were doing all of this in software, it was a more leisurely act, so you can just timestamp at that level. So, so 1588, the other thing it did was it kind of changed the mindset from one where a client approaches a server and to find out what the offset of the client is, to one where masters initiate the transaction and the clients learn their offset. Okay, so NTP was client initiated. In this case, it is server initiated. Okay, so we kind of saw that transaction. So message 1 goes out. The left side is the server, if you may, and right side is the client. So server gets a T1, but it's not able to include the T1 in the sync message, but the receiver gets a T2, timestamps a T2 here, and then T1 follows in a separate packet, and then there's a similar transaction on the reverse side. And then the slave or the client has 4 timestamps, T1, T2, T1 through T4, and very much like the computation we saw previously gets done. But additional measures that 1588 also does is that in order to get more precise handle on network delays, so since part of the network delay is also delays, queuing delays in the switches or routers or other network equipment along the way. So 1588 compliant network equipment, what they also do is when a packet comes in, they timestamp it. When the packet goes out, they timestamp it. They take the delta and then they subtract, they adjust the timestamp which is in the packet. So this way, the delay you get is if you recall the equations, we had the offset and the delay. So the delay that you're getting now is excluding the network, the queuing delay within the network. So again, more precise, basically, things that happen. Experience with 1588, so pretty good. I mean, sub-microsecond with, obviously, because of the clock drifts and all, the rate updates are pretty high, but if you can go down to closer to order of 10 nanosecond or so with sort of better everything, if you may, and you can go down even lower if you are willing to go to the level of calibrating wires and everything like that. Okay, so like Ethernet cable being measured and stuff, so all those things being done. Because in particular, at very fine resolution, even things like the asymmetry in different wires of a cable begin to matter. And the other thing I'd mentioned was that sort of this stuff is being heavily used beyond its original intent of factory automation and all to now financial industry and such as well. Oh, and the other thing is there's work in the space of creating these kind of things for Wi-Fi and sort of wireless protocols also. So so not just limited to Ethernet in this stage. I guess another thing that we saw earlier on was the important role that temperature ends up playing. And I had talked about TCXOs, which are basically oscillators with circuitry in them, which compensates for variations of temperature. So imagine they continually adjust the voltage being applied to the crystal so that you get a more stable output. But you could also attempt to do equivalent stuff as an equivalent compensation at the software level if you have runtime access to a precise clock. So TCXO's mindset is, I want a precise clock, let the factory calibrate and put the special circuitry. But the other alternative is that if you could perhaps do it cheaply by making use of a synchronization protocol to then access more precise clock, or which you then use. So that kind of led to ideas like integrating temperature compensation with time synchronization. But very crudely, what happens is that you will have some sort of a temperature, you will have a temperature sensor, but no other compensation circuitry. The compensation is being entirely done in loop, in software, and intuitively it boils down to that every time you are talking through PTP or NTP or some such protocol, every time you're talking to a server with a stable clock, you are learning the drift characteristics of your clock by fitting those curves that we kind of talked about earlier. And then you make a note of it. So you basically say that for this temperature, my drift is so much. For this temperature, my drift is so much. So after a while, you have learned this. And this thing could be either just a simple table and you do interpolation, or could be something more sophisticated, some sort of a machine learning algorithm which you kind of train. But the point is that later on, you are going to use the temperature to predict the drift, and then you use that as a compensation mechanism without having to go to the server as frequently. So in effect, you get the effect of a TCXO without the cost of the TCXO by doing this online calibration. So these kind of ideas, again, have emerged. Just described one piece of work, which basically I think I have sort of given you the idea. The other thing is these kind of approaches can also compensate for the other effects which affect clock quality also. Like for example, aging, something I mentioned previously also, that as crystals age, there is a change in the frequency that happens. So you can again kind of capture these kind of effects also. So temperature, aging, acceleration is also, because it deforms the crystal. Voltage is another thing which can impact things. So like if you're, for whatever reason, your regulator is not working well, so the voltage is different, that will impact frequency as well. So I'm skipping these slides, but the point I just want to make is that once you have access to a network, and over the network to a stable clock source, and you have a well-designed synchronization protocol, then it can essentially do, essentially you're doing online calibration, so then you can mitigate the need for having a local clock of high stability. So now with networks in cellular systems, essentially you are only milliseconds away from an atomic clock, and you can make use of that in good fashion. And obviously GPS is the other thing that you have access to. Another thing is that clocks consume power. This is something that shown earlier also, but way earlier also, but here also you see that like these things have a power trade-off, right? I mean, so loosely speaking, higher the frequency, higher the power, higher the stability, higher the power. All these things come in your way. So that begins to limit the lifetime of a system. So if imagine if your device you're going to duty cycle it, but if it has to maintain a notion of time while asleep, then the clock has to remain up. And if the clock has to remain up, then the clock's power, the crystal and the counters and all that you have, are going to come in your way. So another idea which therefore gets explored quite a bit is design where you have multiple clocks. The idea being that when you are asleep, you switch to a very low power clock, low frequency, high stability, those kind of combinations. And then you switch back and forth. So if your clock is slow, that's another way of saying that your time is coarser. So imagine a system where you basically say that, look, so two kinds of scenarios imagine. Okay, so one scenario is I want to put the system to sleep, but I want it to wake up at some precise time, let's say 5 p.m. Okay, so one way to approach this thing is you would say, okay, I need to wake up at a precise time. Let me keep my clocking system up, and maybe it's a stable clock, and I kind of synchronize and keep it disciplined, keep it synchronized somehow. Okay, and then I wake up at the designated time. But you could do better. For example, what you can do is you can switch to a more relaxed clock, one which consumes less power but has more drift, and then put some safety margin. And then you go to sleep, and then you wake up a little bit before 5 p.m. and at that point you can resynchronize the clock with the network, or you can switch over from, and you can also switch over to a faster clock. So kind of you have duty cycling the clocks also, and now you have precise time at the moment you need. Another thing, a second thing you can do is that you don't even have to wake up a priori. So let's imagine that your task is that whenever a asynchronous event comes, you want good timestamping of it. Okay, you want to attach a good timestamp to it. So that would normally lead you to think that, okay, so if I have to precisely timestamp, my clock must be up before that, and I should in a good and stable mode. But you can also go backward in time. So imagine a system where when the event comes, if you had a clock which was very rapid wake up, okay? So when the event comes, you wake up your rapid clock and synchronize it, and once it's synchronized, you project it back in time. So once I'm synchronized, I can also retroactively timestamp events that happened in the past, because I do have locally how many clock cycles have passed. So it doesn't have to be that at the time the event came, you should be synchronized. As long as you get synchronized soon thereafter, you can go back in time and subtract things out.
So is it like when a packet comes, I put it like in a stack and then
I make a note of its information. I just start cycle counting. Okay, my local clock. Okay, and meanwhile I'm awaiting my local clock to synchronize. And once it is synchronized, and I also know how many cycles passed, I can basically go back and say the event must have happened at that time, right? So you don't. Yeah, now, of course, this presupposes a bunch of things, right? I mean, it presupposes that I have a clock which is very rapidly can be woken up pretty rapidly. And so that has received a fair bit of attention in recent times. Professor Pamarti's group out here has done some pretty amazing work in that. So they had a paper last year actually they had a paper last week at this week at ISSCC, which is about very rapidly oscillators which can be woken up very rapidly. Okay, so it turns out that sort of previously, since this clock duty cycling is something which has come to fore only in these heavily duty cycle IoT systems kind of devices. It's not something normally you carry in other electronic systems. So so their work kind of looks at this issue that how could I have very rapid wake up clocks, because clocks have to wake up and stabilize, and normally they were designed for like milliseconds, tens of milliseconds type thing, which is eternity in if you are doing precise time stamping. So they have significant improvements there. The other thing is to implement multiple clocks. Of course, a crude approach is to just have a whole bunch of separate sort of things, but you could also imagine doing it more intelligently so that the circuitry is the same and it's just the oscillator which is changing. And then maybe the circuitry itself can scale, like for example, the PLLs which are surrounding the circuitry, maybe they can be tuned on the fly depending upon how stable or what resolution you need. So all those kind of things could be done. This is sort of an early example of kind of ideas one can play with, which is if you can have in the same system a fast clock and a slow clock, and then the idea being that whenever you want to sleep, you switch to the slow clock and you shut down the fast clock, and then if you are waking up on a designated time, like it's a time division multiplex type system, then just prior to the slow clock indicating the time, you are going to kind of wake up the fast system, because the slow clock is extremely coarse. So your wake up time may not be precise if you were to switch to if you were to be on the slow clock only.
If I'm waking up my clock, so even if it's like very fast wake up, it's still like some delay.
Yeah.
So
Yeah.
So can I model that, or is it like?
Yeah, you can, absolutely. And the wake up has to do with a lot of things. I mean, there is the mechanical subsystem of the oscillator itself stabilizing, and prior to that, the voltage stabilizing. So all of that sort of comes, and you place some bound on it, but you try to make it as fast as possible. It's kind of the same thing as waking up a CPU or waking up a radio, right? I mean, that delay kind of matters. Now, in this case, the only thing is that any error, if it is pretty long, that wake up is pretty long, then during that time your local clock is effectively your other clock, right, is basically open loop, right? And so its measurement is not that great. So there are two ideas I'm simultaneously sort of multiplexing out here, right? I mean, one idea is where I have a fast clock, slow clock, and while I'm asleep I have the slow clock, and when the event comes, I switch to the fast clock. Okay, when I'm up, I switch to the fast clock. The other idea I'm proposing is that when you go to sleep, you have no clock. The event comes, then you start the clock, and then you project back in time. Okay, so in that case, you can just truly go to sleep, but you have to design the system carefully. I guess the bigger takeaway out here is that you look at these powers. I mean, these are microwatts, seem pretty low. Seem pretty low, and the more stable, higher frequency stuff is in milliwatts. Okay, so these are pretty high if you think in terms of what impact they will have on sleep time with a coin cell or even energy harvesting system or things like that. So when the system is doing nothing, so to say, then clock becomes your perhaps the biggest power hog, okay, and one therefore has to be careful about it and truly kind of analyze what do you truly need out here. The answer in some cases may very well be that you need to maintain very precise time all through, but often it is not, and therefore recognizing that and designing a system which kind of can cater to these different needs is important. Thus far, we kind of focused primarily on systems where it was single hop time synchronization, and by that I mean A synchronizes to B, and we are kind of ignoring what was happening in the middle. So even though internet obviously is multi-hop, we kind of just treated it as if it was a link whose delay was highly variable, and I was just tolerating it as error in my synchronization. I did talk about FTSP as one protocol earlier on, where you kind of flood the network, right? If you recall, I think it was last Thursday, that a root node sends out a message and it kind of just propagates, and everyone in one outgoing broadcast learns the offset with respect to the root. But this problem of kind of how do you synchronize over a network has received a fair bit of attention, because oftentimes your problem is like the following. There's a bunch of nodes and some of them can talk to each other. So let me jump. Like imagine a network like this, okay, some sort of topology, and my goal is to synchronize them, okay, so that all nodes are on a common time coordinate system. And if that's all I want, then it is basically my choice of coordinate system is arbitrary. But then there is a tighter version of this problem that maybe one of these nodes is a reference node. It has perhaps a GPS attached to it. And then my goal is that all of the other nodes should synchronize with this guy, okay? So how could we structure this thing? So one approach could be like, let's take this one, right? I mean, so we say, okay, this node out here is the server, time server. Then we can use something like NTP, and each one of them synchronizes with this guy. But that kind of seems like redundant, right? I mean, because the messages are passing through these different hops. We could do something like FTSP, where this node broadcasts and floods the network periodically. What I could also do is think of this thing as kind of an optimization problem of sorts. So what I can do is each link, which corresponds to a pair of nodes, they can exchange in the kind of synchronization primitive we talked about earlier. So they can measure their offset, and then so each network link you can imagine now representing an offset measurement. And now I have a bunch of measurements, and now my goal is to find, assuming the offset of the server is 0, what are the good values of assigning an offset to all the other nodes so that I have a best fit. So let me explain that problem. So let's look at this node 5 and 6. So 5 and 6 have a direct measurement. So let's say they measure the offset to be 0.1 second, okay? That 6 is 0.1 second ahead of 5. But they have an additional constraint also, 5 through 7 through 6, right? So offset from 5 to 7 plus offset from 7 to 6 should ideally be the same as offset on the 5-6 link directly, right? So how do we combine this? So essentially I have an over-constrained system now. And usually you solve these kind of systems by then posing it as an optimization problem and minimizing some error criterion. So you're going to say, okay, what is that offset assignment for 5, 6, and 7 that minimizes, let's say, root mean square error, okay? So 5, 6, there will be error, 5, 7, 7, 6, I kind of feed them into an optimization thing and kind of figure out what the error might be. So there are a variety of ways you could approach this problem, because in this case you could have said, maybe I should just focus on 5, 6. But that's not necessarily a good idea. What if the link 5-6 is bad, but the links 5-7 and 7-6 are good? They are low jitter links, delay is more stable, whereas 5-6 may be some sort of a lousy link, in which case I do want to make use of this 2-hop, even though it's more expensive, it's likely a better synchronization. So it's these kind of issues which help drive this setting. And usually in these networks, then the goal is, I mean, you can imagine these kind of networks being there where there is no infrastructure, okay? Oftentimes, like multi-hop topologies are found in sensors in buildings and all, or battlefields, or out in a city. These kind of things are very common. And what you would want is, instead of each one of them individually synchronizing all the way out to some server, to kind of have something specialized just for this. And you could take this notion further and say that, look, I can think of it as a problem of jointly finding location and clock offset, much like GPS does, right? GPS, if you recall, computes X, Y, Z, and T. So likewise, every time you're making a measurement out here, you're really getting a constraint on delay and the clock offset. And the constraint on delay is, another way of saying, is a constraint on distance, right? So I can have each pair corresponding to each network link exchange just 5 sends a message to 6. The act of 5 sending a message to 6, that equation really constrains the distance between 5 and 6 and the offset between time of 6 in some manner, right? And if I were to make such measurement for each one of these, then I have a bunch of measurements, and I have, for each node, I have 4 variables. So I can combine these things again into an optimization problem and say, look, I'm trying to localize this network and synchronize this network simultaneously. So that's kind of the system in its full glory. And you could make use of extra network links, all those kind of things. You can organize the system in many different ways, but you could also imagine 5 broadcast a packet. Both 7 and 6 hear it, much like RBS was doing. And now again, I have some additional constraints. So I can think of, at the network level, you can kind of play these tricks to optimize things differently. Some other people addressing this kind of problem have approached this as, if one wishes to synchronize, this node wishes to synchronize, this is 11, okay, so one wishes to synchronize 11, let me find the best route through it. So some early work also took the route of finding the highest quality route through the network, namely the route which had the best delay characteristics. So variety of ways you can sort of approach it. It turns out that there is a nice analogy between the optimization formulation out here with a lot of circuit problems, Kirchhoff laws and all, okay, so you can actually pose it in circuit theory terms and then find solutions to it also. So variety of ideas both from CS and EE have emerged in this space. The other thing which comes up is that how good your time is synchronized is more of a function of your location in the network as opposed to your geographical location, okay? So connectivity matters more than sort of the geographical separation. So one group which has done a lot of work in this space is Joao Hispana's group at UC Santa Barbara. And what they kind of point out is that it's the logical network, the logical connectivity, as opposed to kind of the actual physical location, which matters more. And how well your network synchronizes is a function of kind of the dimension of the network. Excuse me. So, for example, imagine these 2 networks, okay? In this case, so it turns out that they have the same number of nodes and the number of measurement per edge is the same, except this network synchronizes a lot better than the left network because its logical topology nodes are actually farther away logically over there. So so one of the things, again, this kind of offers as another trade-off opportunity, because in radios you can always communicate farther by transmitting with a higher power. So if you have a wireless network, what you can do is, if you really do need to synchronize better, then you send out your synchronization messages with a higher power so that you're covering more nodes in a single hop. So you could do those kind of games at the network level to adjust to temporarily gain a higher logical connectivity and therefore a better network synchronization characteristics. There has been work on ideas like what are the fundamental bounds on synchronization that you can achieve for different network characteristics and all. So a variety of these kind of things have been explored. One idea that I wanted to bring out, which I all found the work to be kind of cool, was the following. So these guys make use of some physical layer characteristics of wireless to really do low overhead but very precise synchronization by really kind of killing two birds with one stone, so to say. So the problem that they try to address is that, and this is kind of strictly in wireless context, that flooding in a wireless network is a pretty expensive proposition. And the reason it's very expensive is that there is an explosion of traffic that happens. So let's say I want to send out a message to all of you. So of course, if I transmit at very high power, then all of you listen it, the problem solved. But in a multi-hop network, what happens is when a node transmits, only its neighbors hear it. And then those neighbors are supposed to retransmit. So for example, in this case, let's say this node, initiator node, is supposed to send out a packet, then what will happen is that these nodes which are one hop away from it are going to receive it. And then they have to retransmit. The problem is that if we are not careful, then if they retransmit at the same time, then they will collide with each other, and then they will again retransmit, and there is just an explosion of messages happening there. Moreover, there are unnecessary retransmission happening in this process also, which is, so you need to orchestrate this thing carefully. So couple of ways which gets done. One is you put some upfront effort, you figure out some sort of a tree structure along which you are going to send messages. So you kind of a priori decide some nodes which are responsible for transmitting broadcast packets. Okay, so that way we make sure. So we kind of discover the topology of the network beforehand and then designate those nodes. So like for example, the initiator may say that, oh, okay, only the second node is let's see, okay. Okay, so it may select some subset of the second one-hop nodes to retransmit and so on and so forth. So we could do that, but the problem is if these things are mobile and all, then the topology maintenance itself can be pretty costly. Other type of approaches which are done are things like we develop some sort of scheme so that the nodes, one-hop nodes, instead of retransmitting at the same time, they stagger themselves. So like, could anyone suggest me something? Like for example, let's say I sent something, all my one-hop nodes heard it, okay, and I want to make sure in a pretty low overhead fashion that when they in turn retransmit, they don't retransmit at the same time.
That's at a random time.
At a random time, right? That's one scheme. Another scheme would be tie that randomness to address somehow. So like you take your node's address, feed it into a hash function, and take the output of the hash function, use that as your slot. So you basically say, from the point they heard my packet, there are some slots, and we basically are assigning those slots to them. But you let them do it in a distributed manner without any coordination. And the same thing can be done at every stage. Okay, so these are common approaches. What the scheme Glossy out of a group in Italy does is, it tries to do a single pass flooding by leveraging very precise time synchronization, but the synchronization is a side effect of their flooding. Okay, so essentially in their system, every so often on a periodic basis, the system enters into a flooding phase, during which all the broadcast traffic which has piled up at the root node, let's say, is flooded into the network. And that flooding does two things. It disseminates information, but it also synchronizes the network. So let's see how it kind of works. So it makes use of an idea which I had mentioned earlier as a use for time synchronization, and that is coherent combining. Okay, so basically what's happening is that if I have two transmitters T1 and T2, and if they transmit simultaneously concurrently at the same time, then the receiver, generally speaking, is going to get gibberish, because these packets are going to collide and give just result in interference, and neither packet 1 nor packet 2 will be received. But if they were to transmit in a manner which is totally synchronized and the packets are identical, then literally the two signals, two waveforms will overlap and are identically, and therefore the packet would be successfully received. But it requires two things. Content should be the same, which is great because we are broadcasting, and packet should be synchronized. Okay, right down to the bit level, because even if there is a sub-bit or sub-symbol level error, then again we are going to have problems, right? So we need very tight synchronization. These guys are working with a relatively slow radio. So in their case, they needed synchronization of half a microsecond, and sort of then they achieve this thing, and it's broadcast. So the packet content is the same. So that's basically what happens in this case. So the initiator sends a packet, all the one-hop neighbors receive it. Now, normally, in normal things, we would have either said some of these were designated to be forwarders and the others not. That would have required a lot of maintenance effort and all. And the other alternative scheme was some random staggering. Okay, but here, the third possibility is that these guys all transmit together, same packet, but they do it in perfect synchrony. Okay, so I'm assuming that the synchrony is maintained, but in a sense, the same packets that we are broadcasting can also carry timestamps to maintain, to create synchrony. So now in this case, what's happening is that these guys, the first hop nodes, they all transmit identical packets in synchrony, and therefore wherever the packets are received, they are going to be overlapping. Now here there are some assumptions being made. We are also assuming that the difference in distances from different transmitters to a node is also smaller than the symbol period, or much smaller than the symbol period, which in short range networks is going to be the case anyway, because they're working with 0.5 microsecond. So this scheme is really meant for slow speed radios where the bit where the symbol widths are much longer than the speed of light over that distance that you are seeing. But if those cases are met, if those assumptions are met, then it does this clean thing, which is you just literally kind of just propagate the packet down, and you are making sure that there is no collision happening. So, and the next thing that happens is this, and kind of the whole network receives a packet. This is another way of looking at it. So, kind of a timing diagram out here. Initiator sends the packet, the first hop node received it, then in the later time slot, the first hop node transmits, and the second hop node receives it, but it's also received back by the initiator. So this thing serves as a acknowledgement. So the initiator knows that things were successful, and then kind of a pipeline effect. Next packet happens, and so on and so forth. One interesting thing about wireless is that every time you transmit a packet, you are kind of preventing others from transmitting a packet in a geographical region around you. So let's say if I send a packet from A sends a packet to B, then my signal, assuming my antenna is sort of has symmetric signal propagation all around, then I'm also effectively sending the signal to everyone around me. Now, when I send to node B, when B transmits, it will be heard by C on the other side, but it will also be heard by me, A. And this whole process kind of goes on. So this is an issue you encounter in wireless generally also. So what it means is if you have a chain of nodes, A, B, C, D, E, right? Okay, bunch of links, link from A to B, B to C, C to D, D to E. Okay, let's say each link is a megabit per second. And let's say these nodes are lined up in a chain. How many concurrent transmissions can I have in a network? Or so what's the capacity? What the capacity of the network going to be? So let's imagine I have n nodes. So or n plus 1 nodes. I have n wireless links, and of a megabit per second each. So their aggregate capacity is n times 1 megabit per second, n megabit per second. But because of this interference, not all transmissions can take place. So what do you think is the capacity that is actually possible? I'm using the word capacity in a very loose sense out here, okay, not in any fancy theoretical sense. So how much data can the network transport? It clearly cannot be n times 1 megabit per second. How much do you think would it be, and why? So again, let's imagine a row of nodes, A, B, C, D, E, okay, through N. What fraction of the links can be simultaneously active? Huh? Half. Do people agree with that?
Depends on the power.
Oh, okay. Let's imagine they're right at the front. Okay, good question. Okay, good comment. So it depends on the power. Okay, so let's say the nodes are smart. They are not going to send at any more power than 1 hop. Okay, so this node sends, it's heard by this. This node sends, it's heard by, and so on and so forth. Okay, and each node is rate R, and I have n nodes or whatever. Rate 1, I have n nodes. Okay, so how many nodes? So let's think about half. Okay, let's say this guy is transmitting. Okay, so this guy is hearing. So can this guy transmit now? No, because if it also transmits, then I'm going to have a collision out here. Generally, right? I mean, forget about the glossy scenario. So this guy cannot transmit. What about this guy? This guy can transmit. So this guy will, sorry. So this guy can transmit. No, right? This guy cannot transmit. What about this guy? So okay. So let me phrase the problem more clearly. My goal is that I'm going to flood the packets. Okay, so this guy is the initiator, is going to send out the packets, and they have to reach out here. Okay, and think of it like a pipelining problem. How rapidly can I send a packet, right? So I send a packet out here. Now, while I'm sending this, if there was any previous packet in the pipeline, then node 3 cannot transmit it. Node 4 can transmit it, right? So this transmission can take place. Agreed? Right? If I'm pumping the packets out. So what this says is that in something like this, I have only 1/3 the capacity. Right? Not going to have. So wireless, you have all these geographical effects that you have to worry about anyway, and very rapidly sort of you run into problems that your network is very inefficient. But back out here, so really what's happening here is very simple. Just recognizing this idea that if things are synchronized, then I can let collisions happen, and collisions are in that case not bad. Okay, and so I can pump through more easily out here. So in this particular case, you're seeing is because things are synchronized, I am able to pump things every alternate slots as opposed to every 1/3, every third slots. So implementing this, you either have to do some pretty, you have to make sure that whole system is highly predictable, right? I mean, you are trying to transmit these packets, and you got to make sure that these different radios are highly, are taking actions at the same time, okay? So you need radios to which you can say, squirt out this packet precisely at this time. And then also you need to make sure that your notion of time and other notions of other nodes' notion of times, they are all kept in synchrony. The group which did this work, I mean, they put in a lot of effort in writing code, which are very predictable. You can, even little effects like caching effects and all can cause half a microsecond error. I mean, that's very easy to run into. But they pulled it off, and they made extensive use of features from the radio, like for example, the start of frame delimiter signal, which I had mentioned that some of the radios have to provide you timestamping capability. So all of those things they achieved. Main thing is that through this, they achieved 0.4 microsecond accuracy at 8 hops, over an 8 hop distance. So which is pretty amazing for a kind of a pretty low end radio. So so that was one example. Also wanted to touch upon that there's a lot of work in other fields also on synchronization or synchronization like problems. I had mentioned earlier metronome synchronize, I had mentioned firefly synchronize. There are a lot of examples of synchrony in natural systems where, because some sort of information exchange happens, organisms or systems end up synchronizing, and perhaps one could also make use of those also. One common approach of synchronization, which is actually mimicking some of these natural systems, works as the following. It thinks of time synchronization as a problem of consensus. So we wish to agree upon something, okay? Value of a variable. In this case, we wish to agree upon the value of time or value of what frequency it is. So what these so let's imagine if let's say each one of us was making a measurement, and then we want to average it out. So we want to agree upon the average value for it. So there's a class of algorithms. So one way you can approach this thing is you can say, okay, let's all send our reading to a central place, and it's going to compute the average, and it's going to broadcast it out. But there's another approach which actually turns out for a lot of functions works very well, which is what I'm going to do is we are all going to say, this is my average, okay, my current best estimate of the average. So you'll start out by advertising our current value. So if I measure 10, I'll say average is 10. I believe the network average is 10. You measured 12, you'll say I believe the average is 12. And what each node does is every time it gets a message from a neighboring node, it updates its average. So if I heard 12 and mine was 10, I'll say, okay, the average is 10 plus 12, average 11. So I'll say the new average is 11, and I start advertising that. And if everyone does this, it turns out that these type of systems converge. These are called relaxation approaches. So essentially, you can imagine a system like this. Each node broadcasts a local time periodically. Says time is this. Everyone is saying time according to my local clock is blah. And what we do is every time I hear someone else advertising and I compare against my time, if there's a discrepancy, I take the average. I move towards it. So if my neighbor says the neighboring clock is ahead of me, my clock is behind, I'll say, okay, let me advance my clock. If on the other hand neighbor says its clock is behind me, then I'll say, hey, I'm running too fast. I'm going to slow down my clock. So that's all we do out here. So node waits for time t, it collects messages broadcast by other nodes, and for each message receives, it estimates its skew based upon that, and then it updates its clock. And you let this system run, and it turns out that these systems achieve synchrony. Okay, and it turns out that this is how these natural systems work. So like that metronome example, what's happening is a subtle inertial system, so physical signals being exchanged to the table. So if a metronome is moving too fast, then it causes the other metronome, which was slower, to move faster, and likewise a slower metronome causes this guy to slow down. So ultimately everyone kind of ends up synchronizing. It's the same idea. It turns out that was the explanation for fireflies also, that fireflies essentially observe each other and end up into synchrony. Same thing in other systems where chemical information is involved. So there are groups of animals whose behavior end up getting synchronized because they are in close proximity, and therefore chemical messaging happens between them. So the underlying mathematical model in all of these is essentially I have free running oscillators, and those oscillators were originally on their own merry frequency, but they're coupled. So they're exchanging some information, and the information that they are exchanging is basically this model of integrate and fire, okay, model. And this was proposed sort of 30 years ago or so in physics. The nice thing out here is an entirely decentralized model, right? There is no initiator, no server, nothing. The whole system just synchronizes. It reaches a common frame of time. So the mathematical model is like the following. I have an oscillator at every node. Okay, this is a free running oscillator. Some state variable x, and I'm basically saying x dot do time differential of x is some function of x, and that evolves according to this. And what will happen is that if there was no coupling, then all I will see is at different nodes, I'm going to see some periodic waveform, and these periodic waveforms will not be synchronized. They'll be out of phase. But now imagine that I'm able to observe my neighbors, okay? Which is kind of equivalent of receiving a packet broadcast by my neighbor. And if a neighbor of node I fires, then the state variable is updated by a little bit. Okay, so we basically say some function of what I observe from the neighbor, I'm going to attach some. So depending upon the system, you could imagine that could be positive or negative. In this particular case, we're saying it is positive. So if my neighbor is faster, I'm going to attempt to catch up with it a little bit. Okay, so that's the model. So now you have these free running oscillators which are normally integrating like this. So the oscillator, what it does is when it reaches the value 1, it resets. So that's a periodic waveform. But then every time I observe a neighbor, then I adjust the state variable a little bit. Okay, so every incoming packet from a neighbor adds to the add some value to the current state value. So in a sense, what you have is a system which kind of looks like the following, which is there's a free running oscillator component, which is the F function, and then at some moments, the message exchanges are happening. At those moments, there is an adjustment to the state happening among a neighboring system. And you have a network of these things. So everyone is watching their neighbors. It turns out that with very high probability for under pretty reasonable conditions, such systems cause this kind of coupling, cause the phase difference to go to 0. In effect, these oscillators synchronize their phases. So that's kind of the basic idea. So what those guys who sort of described this phenomenon, modeled this phenomenon back in 1990, what they showed was that so there is a dependence upon the initial conditions, but the set of those initial states where the system will fail to converge are probabilistically very unlikely to occur. So for most starting situations, the system ends up converging, and this part was then exploited in wireless networks in a paper in 2004, which basically had this theorem, which basically said that they described certain conditions the network topology has to satisfy in terms of the connection matrix of the network. If those properties were satisfied, then the synchrony would happen. So these guys basically described under what situations, if a network is fully connected, you are good to go, but our networks are not. So it basically gave an explanation in terms of what network topologies will still lead to convergence. But the basic protocol is super simple. It's basically the example of that consensus thing I was saying. You just advertise your clock, and the other ones are kind of averaging them out. And this is kind of a pictorial depiction of that. So kind of nodes start out with all over the map and will very rapidly then by just in this purely decentralized manner. This is kind of another look at it. Starting out on a bit hard to see, but the sine waves are out of phase, but then current and they kind of are in synchrony. So some of the systems that have been developed have kind of made use of this. Mind you though that this thing does phase synchronization. What it is saying is everyone is agreeing upon a time base for this network, but this time base may still have nothing to do with UTC. That will have to be a separate consideration. So if you may, what you may have is one node which is, let's say, has a GPS. It participates in this protocol, does the phase synchronization. It measures the offset between this network time and the GPS time, and then it advertises that somehow so that everyone gets to know what the offset is. But kind of the basic approach works like this, and this is actually quite nice. It's, I guess, regime of applicability is going to be kind of these, let's say, somewhat local area systems. So it's not something you would do over internet scale just because of the traffic it induces. But on the other hand, the nice thing out here is as the membership of your network changes and all, things just adapt. You don't really have to maintain anything. You don't have to know who the server is, anything like that. Okay, just exchange messages and you're good to go. Okay, let's see. Yeah. Okay, so I'm going to not cover the remaining slides on the time side actually, and I'm going to switch to talking about wireless, but since it's almost 5, so let's take a short break and then we'll reconvene.
They ordered some
I mean, they have a link to their website, and it's not on the Play Store.
So the one I downloaded was just yeah, but that was a couple weeks ago. Like, I'm searching for it. I don't know if it's like No way.
I know, right? Like I never run. This is like the first time I actually just jogged for the sake of jogging. And just it's crap. It's nuts. It is for the accurate. I was at like 150 and then there was a measurement. Yeah. I will say that it works a lot better with like when it's on the wrist, it's just
Yeah, I couldn't get it to work consistently on the wrist, so it's on the finger. But if I was like sitting down, like sitting down still, I was able to consistently on the finger.
also I found that on the wrist, it seems to just measure everybody at 50. Like I just like tried out like trying to give one and just like measured everyone at like 50. Which works great actually. Yeah. Not how much they cost.
It's really low. It's really low estimate. So then maybe that's like they can't get everything. And that's like around 40 or something minimum for people to display. Because like I think like elite trap it's really low. And like aggressive car is about 30%. So generally they won't quite miss it. So it might be kind of like if they don't have reading, they might put that like a safe. That's probably what it is. Because they don't detect that. That's alright, because oh, did you test how the technology works?
Kilometers.
Okay.
Yeah.
Okay, let's start. So next topic, looking at wireless in context of IoT, and between this slide set and the next slide set, I want to cover some of the relevant concepts, but also do a bit of a deep dive into Bluetooth LE, which is pretty commonly used to connect sensor type devices to various IoT platforms, so like our smartphones and such. So a typical sort of role of Wi-Fi like wireless systems kind of ends up in IoT context kind of ends up looking like this. So you have at the very edge sort of devices, smartwatches and wearable sensors and such, and they typically use Bluetooth just because that's the lowest power thing that's around. In some cases, they also use very low power Wi-Fi. Some cases they use other standards like Zigbee and Z-Wave, but typically we see Bluetooth as the common thing. They hit some sort of a gateway device, and then from the gateway device, then typically using Wi-Fi, sometimes using cellular, they get to the network infrastructure and all the way to the internet backbone. Lately, there are also cellular is penetrating all the way through. So these different Wi-Fi standards kind of duke it out. Also, each one of them kind of wants the whole pie, sort of say. So you see, Wi-Fi has always attempted to create low power versions. 5G, they talk a lot about IoT, partly because they could have sort of low rate versions of 5G operating with low latency and all the way to the edge. So variety of things. Wireless has many advantages over wireless, needless to say, so which is why it's pretty attractive. While the chips for wireless may be more expensive than the similar chips for wired, but the wires themselves cost money to install and all. They weigh a lot, they restrict mobility, all those things they're kind of obvious. And then additionally, once you have radios, you can use them for a variety of other purposes too. So radios can be used for localization, radios can be used for in a radar-like manner, so you can use radios as sensors. So there are a variety of advantages that radios offer in addition to their role as a communication device. So all in all, you would see that wireless is pretty attractive for this application space. And typically, I mean, this is just an example of Hexaware where you kind of see that in there they have two radios. They have a Bluetooth low energy radio, and they also have a 802.15.4 capability, but not the radio itself. So what they have is they have a chip there, which is meant as the chip to manage these radios, but the only radio antenna and all that they have actually put is for BLEs. It's just an example. Usually these devices have a large number of radios, so Wi-Fi, cellular, NFC, Bluetooth, classic Bluetooth low energy. Some of these things also have a radio standard called ANT. So there are a whole bunch of things that you'll find in these devices, and they kind of just occupy different space. But common to all of them is kind of the same good old radio structure. So I want to spend a little bit of time there to discuss what kind of issues that come up. So this picture I think I might have shown earlier in the course also, but basically every radio you can generically view it as it's sending some radio energy over a wireless channel. There is the electronics part to it. There is a power amplifier which kind of generates the signal which is going out over the channel. There is a receive electronic, and then after eventually you get the outgoing information. So the electronics handle on the transmit side compression, error coding, those kind of things, or channel coding, those kind of stuff, as well as medium access control protocol. And on the receive side, it's kind of just a reverse of that that ends up happening. And I'm sure in your early courses, you would have seen that there are a whole bunch of different modulation schemes and all that get used. So there is the RF carrier, which is the actual band you are transmitting in. So very common for IoT devices are the so-called free bands, something called ISM band, industrial, scientific, and medical use bands. The key thing about, so for example, Wi-Fi operates in that. The key advantage of those bands is that you don't, as an end user, you don't need a license. Typically, in radio equipment, the onus of getting the license from FCC falls onto the operator of the radio. But with ISM bands, the manufacturer gets licensed, and then you can freely use it. So that's decides where your carrier frequency is. Modulation basically refers to how the information gets carried. Nat.
Just really quickly. So at the most simple level, is a radio somewhat like an LRC circuit? No?
No.
No. Okay.
No. So just wait. Next slide. I'm going to talk about it. Okay. Okay. So what? You had a bet with Leon or something? Or?
Yeah. We were just.
Okay. But basically, you think of your RF carrier to be kind of the main waveform, and information is riding on top of it by changing some attribute of that carrier, like the amplitude or the phase or the frequency or something like that. Yeah.
But at the most basic, could you make just a simple oscillator circuit that is attached to an antenna, and therefore you
Sure.
send or not send, and that is your
Absolutely.
Okay.
Okay. Okay. You can. Yes. So you can, that's the simplest form of modulation where I send or don't send the carrier. So I have an oscillator and I'm doing sending, not sending. You could, but radios are, that would be a super basic radio. Okay. So that's basically called on-off keying. That's what the modulation is, but yeah. Okay. And then, but the other important role out here also is that of the amplifier, because your signal has to reach the other side with adequate power so that it can be decoded. It can be received and decoded, and that's why you have the role of the amplification, right? So rest of the circuitry is kind of just plain electronics, but then you are boosting the signal up before you send it out over the antenna. So what happens then, kind of, if we go one level deeper, if you look at a typical radio and its building blocks. So somehow, somewhere on the software stack, you are going to say, send this packet out. And that packet kind of flows down through the TCP/IP stack, the networking stack in this operating system. And finally, it becomes what is called as a frame. Okay, so the distinction is packets are like your IP packets over the internet. Frame is what is over a particular local link that you are sending out. So your packet, like IP packet, fits inside the payload of a frame, or often called as a MAC frame. And you hand that to the radio or any other network interface. And the very first, and it will sit in some queue, and what this radio has to do is, it has to acquire the channel to send it. So it's going to be running some sort of a protocol, and that's what I previously referred to as a MAC protocol, or Medium Access Control Protocol. So now we have encountered, and I'm looking at the transmit part of the radio. Now we have grabbed the channel, we have to actually send things out. So few things happen. We first encode the packet. And the reason you encode the packet is to get resilience to errors that might happen over the channel. Then you modulate the packet. This is what I was referring to as making the information ride on the carrier. And Leon's on-off keying was an example of a very simple modulation scheme, but when you hear terms like spread spectrum and all, they are all kind of examples of different ways of sort of sending a signal out. And oftentimes you don't just directly modulate the RF carrier. You first go to an intermediate frequency, and then you go pump up, because going all the way from your DC signal, baseband signal, to very high frequency is extremely problematic. And then you go through various stages. Eventually, you have an RF front end, which is putting the signal down onto the antenna, and this also includes the amplifier. Okay. Here, you would have, prior to the antenna, you'll have some sort of a switch, transmit, receive. So the MAC protocol will decide, based upon following the protocol, whether it is in the transmit mode or the receive mode. Remember, I had made a comment that radios are usually half duplex. So they're either in transmit mode or receive mode. And the reason simply was self-interference, right? If they were to transmit and receive at the same time, then their own signal is so loud that it will swamp the weak incoming signal that is coming in. Okay? So the responsibility of making sure that we are in the right mode is that of the MAC protocol, and therefore this medium access unit, which is typically some sort of a embedded processor with firmware in it, or maybe a finite state machine which is built into hardware. Okay, so this is sort of make this thing following the standards. The reverse path. So here you have a very weak signal coming in. So you need some sort of an amplifier to make that signal stronger, and you basically go through the reverse thing. You have analog to digital conversion, demodulation, decoding, and then you hand the packet over to medium access control, and it will then eventually pass it on if it passes on the test. This is kind of a very hardware-centric view. What's been happening in radios also is that there was a time when everything to the left was probably analog, but then gradually that boundary of analog to digital keeps getting shifted. Out here I have shown it in between as soon as we leave the baseband, so before what is called an intermediate frequency stage. But in the extreme case, there are even work where the boundary is right here, right at the carrier level. You digitize the whole band, like a big swath of the band, and do everything else on those digitized symbols, perhaps not even in digital hardware. The extreme case is what is called as software radios, where you ship it to some server and you decode it there.
What is the IPSN?
Intermediate frequency. So that's what I was referring to, that you don't go from information which is at DC values in one go to 2.4 gigahertz. You first raise it to some intermediate frequency value, and then you bump that one up higher, so that a single circuit is not doing the heavy lifting.
Consecutive.
Yeah. So like if I have to go from whatever DC to 2 gigahertz, maybe I'll go from DC to few tens of megahertz, and then I'm going to boost that one up to 2.4 gigahertz. So simply because doing things at the RF stage is much more tricky, so there are things you can do at IF far easier. So that's the basic structure. Of course, this is like a super simple view of things. I mean, entire big part of EE basically deals with encoding, modulation, and another big part deals with RF circuitry and A to D converter. I mean, this is basically much of electrical engineering sitting right in these boxes. So, so lots of complexity around it, but deep down, I mean, that's what's going on. So modulation is how you have the information right on the carrier. Encoder is partly to cope with comply with standards and all, but the bigger purpose out here is you encode the information so that it's resilient to any errors that might happen. Okay, so adding parity bits or doing fancier codes and stuff like that to kind of make things work out. So that's at the radio level. If you pop one level up, so now you have these radios. Whenever they send out a message, everyone in the neighborhood is going to hear. So then becomes the issue that how do we organize these radios into a network, and that leads to the issue of like what kind of topology that your network will have, and you'll find kind of variety of things that get used. So one which we more commonly encounter are cellular systems and Wi-Fi systems, and these are all examples of base station or access point type topologies. And kind of the basic idea is that I have some sort of a backbone wired network likely, where there are boxes which are called base stations or access points, and then your mobile device or IoT device, doesn't have to be mobile, it talks wirelessly to presumably the nearest such access point. Okay, so in cellular thing they're called base stations, in Wi-Fi context they're called access points, but they serve kind of the same role, and they themselves are connected through some backend infrastructure, and there might be other boxes on this thing which which in turn manage these boxes. Okay, so in a simple system at home you will not see it, but generally that will be the case. In some cases, these boxes themselves may be connected using wireless links. Okay, and nowadays, if you see a lot of Wi-Fi products, they have switched to the model where so they started out with something called range extension. So the idea was homes which were a little bit bigger to be covered adequately by a single access point, and yet they didn't have a wired infrastructure, as most homes do not. How could I connect these things? So first came something called range extenders, which will basically, I'll have a slave access point which will talk to the master access point through a wireless link. Okay, one hop link extension. And then more lately they have become much more sophisticated, where I can have many such boxes and they themselves follow a wireless network among them, and then your laptop talks to the nearest thing. So they are called mesh networks, and that leads to what mesh networks are. And now they predate kind of this Wi-Fi access points forming a mesh network. So mesh networks started out in military for battlefield, and simply because you couldn't have access points there, okay, and the networks are highly mobile and all. So essentially it says I have a bunch of nodes and I have a link with whosoever I can see, right? I mean, so if I'm within the radio range of node A is within radio range of B, then it has a link between it. So I have this kind of ad hoc, as the name implies, it's unplanned, opportunistic, depending upon where people are, what the channel conditions is, could be moving, these links may be changing. So sometimes you hear terms like mobile ad hoc or MANET, M-A-N-E-T. But these are all examples of mesh networks, okay, that arbitrary topology. If you have any sort of smart lighting system or security system with wireless sensors at home and all, you already have mesh networks at home. That's how they operate, because it's very hard to ensure that everything is within a single hop of a base station type device. The advantage out here is that you don't have to worry about obstacles and stuff like that, because you kind of route around, right? As long as the network has dense enough, you are going to be able to do it. Moreover, you don't plan anything. The topology is discovered and the network figures out how to route things and all. But obviously it's a much more challenging problem than if all a mobile node had to do was to talk to the nearest base station. Okay, so Wi-Fi networks are easy. Now, like I said, in some cases, Wi-Fi newer products over the past small number of years, they have begun to form mesh network among the base stations themselves. In fact, this week or last week, Amazon bought this company called Eero, which is kind of a major mesh network manufacturer. So obviously, Amazon is deep into IoT business, so they are kind of getting into that as well. Okay, so the reality now is these kind of more rich hybrid topologies, where in effect you have kind of internet, the core of the planet, and then at the edges of the internet are these wired gateways. But then after that, the world is quite fluid. Okay, so some devices talk directly to the access points of the gateways. Other devices are part of this mesh and have indirect routes to these gateways. So kind of a much richer thing. And then these devices themselves could be client devices like our watches or phones, or they could be themselves additional gateways, but they happen to be entirely wireless gateways. So lots of products now are in this realm where they're catering with kind of somewhat bigger homes and buildings and properties, and therefore your devices are no more one hop from a gateway. That's one scenario, and the other is your gateways are no more purely wireless. So that's kind of a richer topology, even with phones. So firstly with Wi-Fi, I don't know if any of you ever tried, but there's something called Wi-Fi Direct, which is in your phones, which allow two phones to talk to each other directly without relying on a base station. And there is also something called LTE Direct, which basically is a way using the LTE protocol to devices to talk to each other without relying on the cellular base station. That one is, I think, far less widely available, but it exists. Okay.
Quick question?
Yeah.
So for LTE Direct, could you use that as a base, like let's say you're, I don't know, in the middle of nowhere, there are no stations, you could use it like a two-way radio pretty much?
That was the theory. But like I said, it's, I mean,
Doesn't quite work, or?
it's not quite prevalent. Okay.
But isn't like Wi-Fi Direct that you're basically creating an FTP server, and the other one is the client of the server, and that's the file, right?
Not quite, because the thing is the following. So I know where you're coming from. Are you saying, am I turning my phone into a hotspot? Okay. The thing is, Wi-Fi Direct can keep working even in the absence of that. So it literally creates a separate category of packet. So it's not kind of forming. It's more like stringing a wire between creating a point-to-point link between two devices, as opposed to creating a base station.
Then when you do it, you basically have to clearly define who is sending and who is receiving.
Yeah, so there would be some naming scheme and stuff like that separately on top of it.
If you want to like change the direction, and have to again set it up.
If you were to do with the approach that you're saying of hotspot, indeed you would have to do it. Okay, see with hotspot what happens, right? You're going to set up a hotspot, you're going to tell the other party that this is the access thing. Whereas with Wi-Fi Direct, the stuff pops up in your neighborhood, and then you just connect to it, as long as it's giving you the permission. So if you have an iOS device, it kind of shows, it's called AirDrop or something like that. So that's an example that's operating over Wi-Fi Direct, for example. Okay. So Wi-Fi direct, LTE direct, these are more obscure things and not very commonly understood or used, frankly, but they exist. Most of us rely on more infrastructural things at present. There are also mobile versions of these. I already said MANET, Mobile Ad Hoc Network. That's something that military really likes to have. There is also VANET. Any guess as to what it stands for? VANET? Vehicular Ad Hoc Networks. Okay, so I think a lot of examples of those are pretty lame, like whatever, I'm sharing a movie with your car while I'm driving next to you, but I don't think those are very realistic examples.
Isn't a VANET a subset of MANET?
Yeah, VANET is a type of MANET, but with, I guess you could say, an additional element that there are also roadside base stations also. Okay, so roadside units as well. So yeah, but there are examples where you can have traffic-related information and all, or cars can cooperate in autonomous driving kind of settings, or cars can talk to traffic light infrastructure, those kind of things which people kind of talk about. So when we talk about these ad hoc things, these kind of scenarios, there are several things which are happening. One is the topology is a lot more free-form, okay, so it needs to be discovered. Secondly, since things change quite a bit, okay, so either because of mobility or some other factors, and also you need to adapt. And the third thing is there are implications on how you route things. Okay, so if you look at these systems, my laptop is just purely an endpoint. It's a source or a sink. It's not responsible for routing any packets. But if you are in a mesh setting, that every node is not only a source and a sink, but it's also kind of like a network router, right? Because it has to pass traffic which is going through it, okay? So it has to take much more of a network burden than would otherwise be the case. Another thing is that there is an implicit hierarchy out here, which is kind of similar to what internet does. Internet addresses are organized hierarchically, as you know, right? I mean, UCLA IP address, you can kind of literally parse it, and as you go down the digits, you come closer and closer to a subnet to your local area network. But if the world was a MANET, that's almost like saying, I have a flat routing thing. What's the advantage of this hierarchical routing or hierarchical addressing that internet uses?
You know what path you need to go down to reach a particular device.
Be more specific. What does it make more efficient? In what manner? Okay, let's imagine that there was no structure to addresses. Let's say each one of us still had that IP address, but there was no structure, no hierarchy to it, okay? So 128.97.92.10 may be here, but 128.97.92.11 may be on the East Coast. Okay, so no hierarchy, no structure to this address space. What becomes harder now?
Searching for a path.
Searching for a path. So I will have to maintain a table of every host in the world and how to get to it. But once there is a structure, I can say 128.97, that's there. UCLA, let's say, okay, it's not, but pretend. 128.97.92, aha, this is a network in C's, and so on and so forth. So I can kind of look additional bits and kind of just keep forwarding. So now I only need to store prefixes as opposed to entire addresses. But in ad hoc networks, you don't have that possibility. You have to kind of maintain kind of that.
So just curious, when you do have multiple paths that you could take, how do they, like in the industry, create those types of control lists and things like which path you would
There are priorities. So like if you should look at the routing table of a computer, you would see that so it will say something like, to go to 128.97, send the packet to this particular machine. And then you can have a second entry saying to go to 128.97, you can also send the packet to this other machine, and then they will have a priority attached to it. Okay, now how do those priorities get discovered? either manually configured or that's the job of routing protocols. So in the core of the internet, there's a protocol called BGP, which is kind of used for this purpose. Here, again, in ad hoc networks, which are kind of more local area phenomenon, like mesh network in your homes, for example, you would need something similar to happen, right? Some path has to be discovered. These devices will have to store those little routing tables. Usually in home setting, one of the nodes is still kind of your destination gateway, but not always. Like, for example, I have these sort of smart light switches and motion sensors and all at my home, right? And then there is also a gateway. So sometimes I have things like, when this motion sensor trips, then turn on this light. Okay, now it could be done a couple of ways. One is, everyone just always talks back to the smart home gateway, and it issues the command, so only the communication is happening. But over the mesh, but the communication is always either on the way to to central server or way out of it. So one of those nodes in that case is the server at my home. But the other possibility is you can have peer-to-peer communication, right? I mean, a motion sensor can just send a command directly to. So all those kind of possibilities happen. Other things which become difficult, addressing, discovery, like is that node in the network? All those kind of things become a lot harder in these kind of settings. Okay, very rapidly you have to discover and establish trust, and also things like VANETs are even harder. You are trying to do something with two cars which are just passing by in a transient manner.
So every time I want to transmit a packet over a mesh, I have to first do a discovery. And
yes, in short. Okay. The thing though is that meshes at home are relatively static. So they do a discovery once, and then only if things fail, they do a rediscovery. Whereas on MANETs, they will be done much more frequently because things are moving all the time.
And then do I have to specify the routing?
No. I mean, if a system is well done, you shouldn't have to do anything. You should just have to send the packet.
So let's say I'm like node 1 and I say I want to send this to node 4, and I just like.
You just send it.
Then like.
And your node will know to get to node 4, which is the next hop node, right? So for example, whatever, my routing table may say that to get to node Z, I have to send to B first. B will say, oh, you want to get to Z, you have to go to node X, and node X will say, oh, Z is my neighbor, I just transmit. Exactly like what happens in the internet, but somehow protocols have to arrange for the same thing out here. But the key thing out here is, since there is no hierarchy of addresses, so everyone has to maintain every address, unless you are super smart about this.
That is true, but if you have like 2 or more ways to get to node 4 from node 1.
Again, there will be some priority. You'll discover based upon quality of the link or some other thing. There are good thumb rules you can have, right? I mean, establish like stronger. I will prefer the node which has a stronger signal, for example. Okay. Other things which are often done in these things is that sometimes you use geography as an address. Like for example, let's say I want to get a reading from temperature in my lab, let's say. Okay. So I could simply say, I don't care which sensor gives me the value from my lab, as long as it's a sensor which does it. So I can send an initial message purely based upon geography. Okay, I know my lab is whatever, southwest of here. So I'm just going to send messages towards the southwest until it hits my lab. And then within the lab, there could be some discovery process and say, okay, is there a temperature node? Get the reading and then kind of head back. So variety of ways. Look, this is an area where there's probably a 30, 40-year body of work. A lot of early work happened here at UCLA. That's what professors Len Kleinrock, Mario Jerdla, these guys did a lot of the pioneering work in this space. But things are still ways to go because these systems continue to be, it's a very challenging problem, okay? Every problem about networking becomes amplified. So to this date, there is like the conference is entirely dedicated to this topic. Okay.
So, like you said that we also take into account the quality of link between.
For example, I was just citing it as a rule of thumb.
So if I have a magnet and I have to send a message up to it, so first I do a discovery, I do some algorithm to find the shortest path, DFS, or something like that. And so then like, do I send the whole thing like I want it to go by like, follow this path to the next node?
Okay, every imaginable scheme you can imagine exists. Okay, the question is which one. So firstly, can someone suggest to me the stupidest way imaginable to send a message to a particular node in the network?
The longest way possible.
Huh? Flood the network.
Yeah.
Right? I mean, if everyone gets it, then of course my distant node will also get it. So I'm saying, this message is meant for X, and I'm just flooding it, and the receiver does a filtering. It says, am I X? If not, throw away the packet, right? So you could certainly do that. Okay. On the other hand, you could be other extreme. Other extreme is that at every node, to get to every node, I have the entire path. So to get to node X, my routing table will say, go to A, to B, to C. So my packet carries the path in it. That's the other extreme. And as you can see, the first scheme has very little a priori overhead because I don't have to maintain any routing. There's no routing protocol, but there's a lot of runtime overhead when I'm actually sending the message. Whereas the second scheme is exactly the other way around, right? I mean, I'm putting a lot of effort up front to get the complete pathway, but then at runtime, my packet knows how to get to it. Now the problem with the second one is, anyone?
Latency?
Huh?
Latency?
No, actually it's faster. It's not
What about
latency.
if you can't like get to that specific route, or like?
Yeah, because my information is obsolete, right? So by the time actually sending the packet, that path may not exist, right? So these are the trade-offs. Now, fortunately for home settings, things are relatively static. I mean, once in a while, like for example, at my home, every November, December, I put up Christmas lights, and they're all on my these things. So at that time, the network changes, and it takes the system bit of a time to discover the presence of these new entities and kind of presumably optimizes to it. I don't have much faith on kind of routing protocols they use, but let's say it does, and then it works. And then when I'm some spare time, I take them down, again the network changes. Those are probably the only two events that happen at my home changing things. Most homes are presumably like that. Maybe you buy a new product, you install it. But the military setting, factory settings, VANET, these are obviously at a different degree of changes that are happening. Okay, so that's a topology part. The next up is link sharing. So now we have these topologies, and these I have now from various types of links depending upon the topology. That's where the MAC protocols or medium access control come in, and they're fundamentally playing the same role as the schedulers that we discussed earlier in the course. In fact, they're exactly the same thing. I have a shared resource. Instead of a CPU, it's the wireless link. I'm basically trying to decide who gets to run on it, except that running here comes in two shades. There is transmit and there is receive, but other than that, it's kind of the same thing. Same kind of issues, deadline, periodic traffic, aperiodic traffic, exactly the same kind of thing. One big difference, preemption is not possible. I can't, we discussed this way earlier in the course also, I can't stop the packet in the middle and start exactly where I left off, okay, as I could do with a computation. If I stop the packet in the middle, then there is additional things that I'll have to do to make it happen. So on a wireless link, I need to have multiple parties share the link in some manner. So in some dimension, they need to defer the transmissions. So one clear one is maybe my link allows transmission at different frequencies. And so I can divide my spectrum into frequency chunks and then hand it over to different packets. The problem is that the frequency allocation is relatively static, so it's very poor utilization. If I give frequency 1 to IoT device 1 and frequency 2 to IoT device 2, if IoT device 1 is relatively idle, that frequency, that part of the spectrum is underutilized. So what you want is some more fluidity over time. So sharing over time is another option, which is what you do is now you can say, okay, everyone is on the same frequency, or maybe I have a set of frequencies and a whole bunch of people are on one frequency, and now we create a protocol. That's our scheduler, right? So you can think of frequency division to be like, I give each process its own core. And you can think of time division, time-based division as equivalent to our, let's say, rate monotonic or EDF or this kind of schedulers, right? Single processor, whatever. I'm putting multiple things on the same thing. Illusion of parallelism that we are giving. So what fundamentally MAC protocol does is it decides when and how each node can transmit. There's an additional complexity with MAC, which is distributed. I have pieces of MAC software scattered over a bunch of nodes, and somehow I have to achieve this effect as if they are able to coordinate. Life would be very simple if my MAC protocol could run at a single place, and then it could say, okay, now your turn to transmit, now your turn to transmit. It can't do that, right? Because that in itself requires some communication. So, so when it comes to time, there are two broad ways of handling things. One is you divide into time slots and then permanently assign time slots. But then we are back to the same problem. If someone cannot use the time slots, then it's wasted. Or alternatively, you can let them compete, like a packet request arrives, and then I decide when can it transmit. That's closer to our task scheduling model. So this slide kind of an attempt to sort of give you a sense of how wireless links get shared. So I essentially have this time frequency space, and one thing I could do is I can basically do a static scheduling. This is like my static scheduling. And this works fine if my traffic is relatively predictable and non-varying, so like a sensor which continually streams, for example. But most of the things are not, so then you have some sort of a demand-based assignment. When needed, then I assign. And this is where you can have like schemes which randomly access the channel, the schemes which follow some schedule, and a variety of other ways like passing tokens around, like now it's your turn, all those kind of things. So there's again, ever since wireless have existed, these schemes have been studied and around. So again, from early 70s, when wireless networking work started. So let's look at, as an example, Wi-Fi. And while it's a very particular system, but basically 802.15.4, DSRC, which is what used by vehicles, they all kind of follow something like this. Okay, they're deep down, they're not all that different. So in the wireless MAC protocol, this is what happens. There is a free layer, obviously, and that's your radio. The lowest level, they use something called carrier sense multiple access with collision avoidance. This is kind of a variant of Ethernet, okay? And then on top of it, they have two ways nodes can work. One is a purely asynchronous method. Packet request can arrive anytime, and then the protocol handles it. And another one is for time-bounded things, okay? Some combination of that is there are some things like voice traffic and all which need a more predictable behavior. So that's how these things look like. I mentioned that this is like Ethernet. Anyone, I'm sure some of you at least have done networking courses, and therefore might recall what happens on Ethernet, how does it share things. Anyone?
CSMS-CD.
Okay, CSMS-CD. So what happens there?
It listens. So it keeps listening. So in case if it starts transmitting and hears someone else transmitting, it knows that collision occurred, and then it backs off.
Right. So what's exactly right. So I'm just going to elaborate on that. So what happens in Ethernet is, if you have a packet, you're a host, deep down the Ethernet card, what it does is, it says, is anyone else on the channel? If not, I'm going to start transmitting. And also I'm going to listen to see whether my transmission is going through. So I'm going to transmit and also keep listening. And if I receive back what I'm transmitting, that means my transmission is going through fine. That doesn't work with radios. Why does it not work? Something I said earlier in the class? You can't listen while you transmit, exactly, right? So CD part will not work, right? And in fact, even if I could listen As in, even if I were to monitor, the problem would be that my own transmission will totally swamp out the weak signal from the other side, so I will not even detect that there is a collision happening. Okay, so that's why they have collision avoidance, and it's more of a statistical game that goes on. Okay, so this is how it works. So you have a source, it needs to transmit a packet. So a packet request comes, the CPU handed over a packet. What it does is, it waits for a bit of a time. And you will see these kind of things called something IFS. IFS stands for interframe spacing, okay? And the first letter is for different kind of spacings, okay? So there's basically a tiny parameter called diffs. It says wait for diffs time. And if the channel is clear, so you're listening for diffs time. And if the channel is clear during that time, then you start sending on the data. And anyone else who arrives during this time will say, aha, channel is busy, and therefore. But however, what might happen is that two sources may decide to wake up at the same time. Like they both came at the same time, monitored, they both found the channel free, and they both started sending the data out. And if they are nearby, then the packets will collide, and the transmission will not be successful. So that will have to be handled separately. Now let's look from the perspective of a receiver, of a transmitter who was unlucky to arrive a little bit later, when the data transmission is already begun. So he'll wait for a diffs time and wake up and find the channel to be busy. And what he'll do is, he will then wait. And he will wait for a certain time, which is defined by the other transmission finishing, certain idle time in the channel, and then a certain random time where it waits out here. So this is what the other node is doing. It waits for the transmission to finish. It waits for an interval of time because remember that's the waiting time, and then it waits for a window of time, contention window. So it basically selects a random number within this contention window and will pick to transmit from that. Why do you think we make these other nodes do that? Why do we make them wait this additional random time? Why not just start transmitting immediately?
Just in case he clears a response.
So the response is what is being taken care of by this spacing, right?
So all the packets that have been sent are received.
Does it have to do with a sampling rate?
Of what?
A sampling rate?
No. Imagine if my network was heavily loaded and there were a whole bunch of others. They all differed, and if I were to not do this, they would all begin to transmit at the same time. And then I will have a problem, right? So under heavy network, so you want to separate them out. So the same reason why in flooding we were doing randomization is the same idea out here, that you want to avoid the synchronization between those waiting receivers. You want to desynchronize them. And that's what this thing is doing. Yeah.
So then let's call it contention window.
Mm-hmm.
Would the contention window be different for the other senders? Because when you still run into
Yeah, so I mean, pictorially I'm not able to convey it very cleanly, but basically what happens is contention window is a number, and you say I have that many slots, n slots, and you toss a coin, select a random number between that, and then you select that slot, and you will say I will transmit in that slot. But if someone beats me to it, then again I have to wait.
So the contention window is basically the coin flip.
Yeah, it's a random delay.
Right.
Okay, and one thing that changes is that this contention window itself is expanded. So like if I tried and first time I failed, next time I'll try a larger window, because the idea is that this network needs to discover what is the right size of contention window. If it's a very heavily loaded network, you want large contention window, long contention window. If it's a light network, then long contention windows will cause inefficiency needlessly, right? So you want, you start out with small one and then you expand it. Okay. So the question is,
Yeah, I was gonna say, so in a direct link, like Wi-Fi direct, then you technically don't need one? There's only two devices? And
well, remember, the thing is, these things are still shared. Okay, fundamentally it's a shared channel, so even though you have a Wi-Fi direct link, it's a logically direct link. There are other players on that same channel still. And there are additional FCC rules which govern that thing also. Like for example, you can't say, oh, there is another radio present, I'm going to blast things out at an even higher power. You can't do that. There are all these sort of limits that sort of influence this. Okay, so let's stop at this point. I'm going to pick up this thread and then Bluetooth on Thursday. And again, probably remind that from now on we are going to make use of the Friday slots. Okay, and so the Piazza email that I sent out.